Okay, so let me talk a little bit about 7.6. This is the section where we talk about what happens with these systems of, these linear systems of differential equations that we've been talking about that we solve with eigenvalues and eigenvectors. What happens when the geometric multiplicity is less than the algebraic multiplicity? So maybe you have an eigenvalue of multiplicity 2, but there's only the eigenspace is only dimension 1. So that's what we're going to talk about. And let me start. I'm going to teach through this example. So let's just try to do our thing on this. Like the matrix A would just be these coefficients, so 1, 1, 0, 1. So, and then, yeah, I do eigenvalue, eigenvector stuff to this, so I'm doing 1 minus lambda, 1, 0, 1 minus lambda. This is easy. This is 1 minus lambda squared minus 0. So then what I should do is I should not multiply this out. Actually, this just tells me that lambda equals 1. And it also tells me that lambda equals 1 is a repeated, this has a algebraic multiplicity of 2 because of this 2. Okay, so let's find eigenvectors. So how do we do this? I subtract lambda down here, and I set up my augmented matrix with zeros here. And yeah, I guess this is already in really nice form. Yeah, so what would I say about this? This is a leading, so if this is like the V1 column and this is V2 column, V2 is a leading variable here, and V1 is free. Because remember, a free variable is it's really just any column that doesn't have a leading 1. This column does have a leading 1. This is the 1 that is farthest to the left in its row, so this is a leading 1. Anyway, what this tells you is that V2 is 0. V1 is free, so I can let it be whatever I want, say t, and then the eigenvector is like t0. Or we've done this a bunch of times. We know we only need one eigenvector for this, so let's just use 1, 0. But look what happened. Lambda had an algebraic multiplicity of 2, and then when we found the associated eigenspace, we found a one-dimensional eigenspace. This is just a single vector. Roughly speaking, what we should see for a two-dimensional eigenspace is it should be one of these where we parametrize it in terms of s and t. There should be 2 free variables, not just 1. The number of free variables is the dimension of the eigenspace. So we are in this situation. And this can happen. The geometric multiplicity can be less than the algebraic multiplicity. So I'm going to tell you what we do, but before I do that, and because I like this example, because we can do this example another way, I'm just going to sort of trail off here. We're going to momentarily declare defeat on that method. Why don't we just look back at the original 2 equations and just kind of try to think about it, use our brains. Actually, the second equation involves just y. So this is a very simple differential equation. And maybe I won't show all my work here. There's a million different ways to solve this. For example, this is separable. This is like one of the first types of differential equations that we learned to solve. What you're going to get is that y is exponential and it can be times any constant. And then now that I know that, the solution to the second one, maybe I can plug that in the first one. Are we blurry? Okay. So x prime equals x plus c e to the x. And what is this? This is another type that we know how to solve. Now that this involves only x, is it? Well, I think we'll be able to solve this. Oh. I made a mistake. The x and y are dependent variables. T is the independent variable. This should have been c e to the t. When I solved the first one, this is derivative with respect to t. This should have been a t. There we go. That's what I was doing wrong. There we are. Okay. And this is a linear, this is just a, yeah, I guess there's so many types of differential equations that we've called linear, and they all have a commonality. That's why we use the word linear for all of them. This is linear in the sense that we originally used the word. This is a first order linear differential equation. It's like x prime minus x equals c e to the t, and right, if you remember, we have like our p of t and our q of t, and there's going to be an integrating factor. The integrating factor is e to the integral, like e to the antiderivative of p. So p is just -1, so its antiderivative is negative t. Right? I multiply both sides by that. When I multiply the left by the integrating factor, what it's supposed to be is the integrating factor times x prime. And if I multiply the right by that integrating factor, e to the t cancels with e to the negative t, and I just get c. And now I do the antiderivative of both sides. So e to the negative t x equals ct. Yeah, because remember, this is an antiderivative with respect to t. And since I did antiderivatives on both sides, I should put a constant on one side, so say plus d. And now I can solve for x. X is c t e to the t plus d e to the t. And since I'm kind of trying to state my final answer, let me throw y in there too. So we're able to do this one. But maybe you're wondering, like, what does this have to do with the eigenvalues and eigenvectors? There is an eigenvalue and eigenvector way to do this one. And let me try to show you that now. But I like this example because we were able to get an answer one way, and then now I'll show you the new way with eigenvalues and eigenvectors, and we'll see we get the same answer. It's nice to check new things against old things that you know. So what am I talking about? So I just opened the book to section 7.6, and I'm basically skipping to the important part. I'll give you like a little bit of theory about why this works in the next video. But for now, let me just point you to here. This is page 441. What this is, V1 is an eigenvector of the original matrix. And yeah, don't look at this equation. I'm not the biggest fan of the way the book wrote this. Look at this equation. So once again, V1 is an eigenvector of the original matrix. V2 is a solution to this equation. And then what you do is you have two linearly independent solutions. So your general solution is going to be like a constant times this one plus a constant times this one. And what are these two things? The first one is exactly what you would think. Lambda is an eigenvalue and V1 is the associated eigenvector, or it's an associated eigenvector, I should say. And this is just what you do. This is what we were doing for when we were doing eigenvalues and eigenvectors, and nothing weird was happening. It was always just like this. This one is the different one. You take V1t plus V2 e to the lambda t. And like I said, these are two linearly independent solutions, so your general solution is just a constant times this one plus a constant times that one. Oh boy, how long has this been blurry? Okay, sorry guys. Of course, obviously it's really going to help if you are looking at your book at the same time. So sorry this gets blurry. I'm going to try to figure out a way to fix it. This is annoying me. But I hope it's not too bad for now. So let's do it that way. Let me just, let me just write down what we're supposed to get. Because the important thing here was that A minus lambda I times V2 equals V1. So, where are we? We had started trying to do this one the eigenvalue-eigenvector way, and we did find an eigenvector. We can use that as our V1. Now let's use that and try to find V2. So what is this equation? A minus lambda I, we do this all the time. That's just subtracting lambda down the diagonals. If you remember, this matrix was A, lambda was 1, and so that's A minus lambda I. And let's say that, like, V2 is, oh, well, I don't know, A1, A2, and V1's just the first eigenvector that we found. So that's what we do. Okay, this is, I could have done this a smarter way. I just make an augmented matrix and I put this vector here. Yeah, so then the solution to this is, I guess that this equation is just telling me that A2 is equal to 1. And A1 could really be anything. I could set that equal to t. Why don't I just set it equal to 0 or something? Usually I don't set it equal to 0 because I want to avoid the 0 vector, but A2 is already not 0, so I won't get the 0 vector. So, how about that? That can be V2. So then what would we get back to the book. Maybe I'll move this up here and the paper down here. Go unblurry. We have these two solutions, this one and this one. And let me go ahead and write my general solution. So I'm going to write a constant times this one and a constant times this one. So let me write C1 times, and then this is V1. V1 was, I'm looking all over the place here. V1 was this one. So 1, 0, e to the lambda t, and lambda is 1. Okay, so that is C1 times this one. Let me do C2 times this one. So C2 times, what does this say? V1t plus V2? So 1, 0, t plus 0, 1, e to the t. Okay, and let's do one last thing. I would like to check this answer against the other one that we got. Let me combine, I'm going to completely combine these vectors. Can I do this in one step? So in the top coordinate, I would have C1 times 1 times e to the t. I would also have a C2 times 1 times t times e to the t. So C2 t e to the t. On the bottom coordinate, I have nothing from here, and from here I would just have a C2 times 1 times e to the t. So C2 e to the t. And look, the solution we got the first time was this. So it looks like it's just like a renaming of our constant. The one that we called C here is the one that we're calling C2 here. And the one we're calling D here is the one we're calling C1 here. And it's the same thing. So it's good to, because one reason why I do this, I do the problem in two different ways and check the answer against each other, is because in this class, sometimes, well, more than sometimes, I'm pretty light on the theory, so I'm showing you that this works, or at least I'm showing you that it gives the same answer that we were expecting. I'll give a little bit more theory next time.